Good morning. We are going to be looking at fluids for the next couple of lectures. We've done all of these, we've looked at objects, and the objects tended to be solids, and so we had a well-defined object. But what happens if you've got, like in this picture, you've got all of this water, all this ocean water, and how do we do physics on something that's just spread all over the place? So a lot of our common fluids, one of the most common fluids we'll be looking at is water. Another common fluid we're going to be looking at is air. And so gases and liquids fall into this category of fluids. Let's take a look and see what we've got in the chapter. Very quickly here with the octopus, notice that there's a force diagram set up. And so with the objects, the solid objects here, the octopus has a gravitational force acting on it. I don't know if they got the center of mass on that or not. I mean, here's the octopus's head, I guess, and the center of mass is probably over here. But we got a gravitational force, and then we have this thing called buoyant force. So one of the most remarkable things we run into with fluids is that you can float things, right? Or in the case, even if something is submerged, there is this upward force we refer to as buoyant force, and we're going to spend a good amount of time looking at that. But that's an interesting effect. So because of the fluid pressure, the way that the fluid pressure is working, we end up with a net upward force. So that the scuba diver has an upward buoyant force as well as a gravitational force. Okay, and that's what some of the force diagrams are going to look like in this chapter. Now here's our list of topics. We'll move through those. So we're moving on, and first of all we want to talk about the phases of matter. So we think of three common phases. Now there's other phases that are more complicated than these, but if we think in terms of just the basic three: solid, liquid, gas. A solid has a definite shape and size. So we think of a solid as being more or less rigid. Now, not perfectly rigid. We saw in the last chapter everything has elastic properties to it, but more or less a definite shape and size to the object. Liquids have a certain volume, but their shape can change. Now, when you think about liquids, well, let's just move on to this next line here. A liquid is not very compressible. So liquids tend to maintain their volume even as we move them, say, from one container to another. If I take some water and I put it in a container and then I pour it into another container, the container has a different shape to it. But when I go in and figure out how much volume it's taking up in each of these containers, it's basically the same. And that traces back to, and I should have written it in here, you guys could write it in, liquids tend to be non-compressible, or very difficult to compress. Again, we saw in the last chapter that everything has elastic properties, so we can take a sample of liquid and we can put it under a lot of stress and compress it, but not very much, not very easily. Now gases, as a contrast here, gases change their shape, but gases tend to be easy to compress. So I can take a sample of, some sort of air, for example, and I can pump more air into the same volume container. The air will be under greater pressure, but the volume changes significantly when we do that. So again, let's think of this. Solids and liquids tend to be non-compressible, or not very easy to compress. Gases tend to be very easy to compress. And we think of that in terms of the molecular structure, right? The atoms and the molecules making up the solid are in some kind of a definite pattern. The chemical bonds are holding the molecules into a certain pattern, and then molecules attached to other molecules also maintain that particular pattern. In liquids, water again, you've got water molecules, but they're able to move past each other. So the molecules can, unless the temperature drops, right? So you can have, water's a great example too, because under kind of common temperatures, water could be a solid or a liquid or a vapor. So we could have all of these examples. So the water molecules can be locked into place. Where they're a solid, they can be free to move past each other where it's liquid, and then they can be separated into individual gas molecules where it's a gas. So we're going to be looking at liquids and gases in the chapter. Now, a couple of properties that are going to be very important to us are density and pressure. So let's start with density. We've looked at density before, but now we're more interested in keeping track of densities of materials. We'll see that in the chapter there's going to be a lot more times when density comes into our formulas. We're going to be working in terms of density. So let's, density is mass per volume. So that means for a fluid, I take a certain volume of the fluid, measure what its mass is, and I can use that to determine the density for that fluid. Once we've got the density figured out, we can continue to use that density for the liquids because they're not easily compressed. With gases, we have to be a little more careful. But mass per volume. Now, the standard unit for density is kilograms per cubic meter. Cubic meters are like this, right? If we go back, and cubic meters are pretty big. So cubic meter is a lot of a fluid, a lot of a liquid. A lot of times we'll be using grams per cubic centimeter. So we got to be clear on how to convert back and forth, and you can try this on your own. In converting from grams per cubic centimeter as density units to kilograms per cubic meter, we have to convert the grams into kilograms. That's a factor of 1,000. There's 1,000 grams in a kilogram. And then we have to convert the cubic centimeters into cubic meters. And that turns out to be a factor of 1,000,000 because there's 100 centimeters in 1 meter, and those get cubed. So if I take that factor of 100 and cube it, that's going to be 1,000,000. Now, we've defined grams. Grams are defined in terms of the density of water. Water reaches its highest density, surprisingly, not at 0 Celsius, but at 4 Celsius. So at 4 Celsius, that's when the liquid form of water, the molecules of water are as compressed as they become at any particular temperature. And so because of that factor of 1,000 we talked about, the density of water is defined to be 1 gram per cubic centimeter, or equivalently 1,000 kilograms per cubic meter. So again, if we think of that cubic meter, that's a meter this way, this is a meter this way, it's a meter that way. It's a pretty good sized box. If that's filled with water, that's going to be a ton. It's going to be 1,000 kilograms. All right, and then the textbook brings in this idea of specific gravity, which I guess you need to know. I'm not going to be using that a lot, but specific gravity is a ratio of the density of something compared with water. So on this specific gravity, which is kind of a crazy name, I don't know who came up with that name, it's really a measure of density. It has nothing to do with gravity. It's just how much mass we've got per volume. So it doesn't relate to gravity. But water has a specific gravity of 1. Something that has 5 times the density of water would have a specific gravity of 5. So it's just a number that we can throw out to say how dense something is compared with the density of water. And since water is so familiar, it's a pretty handy reference to work with. Here we go. Here's an example. Mass, volume, density. Let's take the mass of a solid block of iron, or a sphere of iron. It has a radius of 18 centimeters. What would the mass of that be? So here we go. Here is an iron sphere. Now, as always, be careful with radius versus diameter. Read the problem carefully. Don't lose a factor of 2. In this example, they did say radius, right? I'm pretty sure. Yep, radius of 18 centimeters. So what we can do is start with our formulas. Actually, I start with a drawing. Here's the mass. there's that radius. We're reminding ourselves it's iron. Our formula for density says density is m over v. Now, they wanted us to find the mass. And so manipulating this equation gives us the mass is equal to density times volume. Now, the volume for a sphere, 4/3 pi r cubed, and r is 18 centimeters. This is a pretty good sized piece of iron. I'm going to convert that over into meters, anticipating that the mass is going to come out to be really, really pretty high. So 18 centimeters, it would be this size. So I'm thinking the size of this block of iron is 36 centimeters across, maybe something like that. So to get an idea. Now what we can do is we can look up the density of iron. I don't think they gave that in the problem, right? So this is something we look up. Now the textbook, of course, has a table of densities in there that we can work from. If it's not in the textbook, then we can look it up online as needed. So 7.874 grams per cubic centimeter. So that would be a specific gravity of 7.874. How dense is this compared with water? Water is the reference, and water has a density of 1 gram per cubic centimeter. Now, I got to get those, as we talked about, I got to get the grams converted to kilograms. So 1,000 grams is a kilogram. And then I got to get the centimeters converted to meters. That's a factor of 100, and that gets cubed. So at the end of all this, I'm multiplying that number, 7.874, times 1,000, the overall effect, and that's coming out in kilograms per cubic meter. Try that out and, make sure you step through these things and you understand them clearly before you start to use any shortcuts. Make sure you understand why it's a factor of 1,000. So 7,870, so if I had, and again, this is per cubic meter, so if I had, that much iron, it would be, almost 8 tons of iron, because cubic meters are pretty big. That's a pretty big size of something. So now I went back, I can't believe I did this, but I did. I went back and I used 18 centimeters here in the volume, plugged that into the formula. I ended up with a volume of this sphere as 24,429 cubic centimeters. So, you can do this in centimeters or meters, either one. And then for the mass, I took the density. Now, since this was in cubic centimeters, I think what we're going to do is we're going to use, for the density, we'll use the grams per cubic centimeter value. So that's the 7.874 grams per cubic centimeter times the volume in cubic centimeters. The important thing here is that these cubic centimeters cancel those cubic centimeters so we can verify units. And what we're left with are grams. Now this worked out to be 192, and I kept too many sig figs, I'm sorry, I apologize. 192,350 grams, which I rounded to 3 sig figs as 192 kilograms for this iron sphere. All right, so that's density. Let's move on and take a look at pressure. Pressure is another really important property for fluids, right? If I have a fluid, a lot of times I don't know how large the sample is. It could be the Pacific Ocean that we're talking about, and I want to be able to imagine different volumes of that, even though it's a very expansive sort of sample. And so throughout that sample, we can talk about how dense it is and how much pressure there is without specifying a particular volume. So pressure, if you remember, is force per area, and the units on this are officially, so here they are, newtons per square meter. That's what we would get by taking a force per area. Now, there is a standard unit that we call the Pascal, and maybe you've run into this, maybe you've heard it on weather forecasts or something. Pressure is a scalar. The units of pressure in SI are pascals. So 1 Pascal is 1 Newton per square meter. And I'm going to use both. Sometimes I like seeing the newtons and square meters in there to remind myself it's a force per area. But pascals also works. Now, a third set of units that I added in, and then I highlighted this, is these units are also the equivalent of a joule per cubic meter. Imagine taking this set of units, multiplying the numerator and the denominator by meters. That would give us newtons times meters on top. And newtons times meters are joules. On the bottom we'll have cubic meters. Now, why joules per cubic meter? What is that telling us? Well, joules per cubic meter would be an energy density. It would tell us per cubic meter how many joules of energy do we have, and you're thinking, well, what kind of energy are we talking about? And it's energy in the compression of the fluid. So what happens is, if we compress the fluid, if we put it under higher pressure, actually it's not very compressible. By compress here, I'm thinking if we place a compressive stress on the fluid, volume doesn't change much, but the pressure will. So the pressure is going to go up when we attempt to compress this fluid. And when we do that, when we put it under higher pressure, it compresses a little bit, and that stores energy. During the decompression phase, where the fluid pushes back out to its, its comfortable density or volume, that's going to release energy. So that's telling us how much energy is going to be released. So energy density, and that I am going to use. So I'll use all three of these units. These are all standard units, and they help guide our thinking. And so, it's good to think in terms of all three of those. Here's an example. So calculating pressure. Let's say that we have a 60 kilogram person, and they're standing. Okay, so we got a 60 kilogram person. I'm more than 60 kilograms, but I'm standing, and I've got my feet on the ground. Now the normal force, up until now, we've talked about gravitational forces and normal forces. It says if I'm standing on both feet, how much pressure is there at the location of the contact, and then what happens when I lift up one foot, right? So if I'm standing on 2 feet, then the normal force is spread over the bottom surfaces of my foot. And it says here that that would be 500 square centimeters. They've come in and measured my feet. 500 square centimeters. I guess, yeah, I guess that would work. 10 centimeters would be like that. And so 100 square centimeters would be a square that big. And yeah, I probably have, some number of hundreds of square centimeters of my foot in contact with the ground. Now, what happens when you lift 1 foot? Well, if you lift 1 foot, then all the normal force is coming from that 1 foot. So here are the drawings here. So I drew some pretty good sized feet. Here's the person. There is a normal force of the person pushing down on the, that's what I'm doing. I've got a normal force acting on me upwards, but there's also a contact force of me pushing down on the floor. And so that's what I'm showing with this force. Now here's the force diagram for the person. There's a normal force, there's a gravitational force. The gravitational force is coming from all parts of the object. We can treat it as if it's all coming from the center of mass, but it's really coming from all parts of the object. And then the normal force is only coming where it's in contact, right? So if I jump up in the air, at least the time that I'm not in contact with the floor, the normal force is gone. When I come back into contact, the normal force is back again. And it's only at the locations where my foot is in contact with the ground. So what we can do is, let's see, there's a mass of 60 kilograms, there's gravitational field, this is Earth, 9.80 newtons per kilogram. That says that in this force diagram, N needs to be equal to mg. Now, mg works out to be 588 newtons based on that 60 kilograms. So it says that the normal force is pushing up 588 newtons, and I would imagine if I'm on 2 feet and I'm kind of balancing myself on, then that's evenly spread between the 2 feet. And then in more detail, we can say what is the pressure associated with that particular force. I can take that force and spread it out over the area. Now the area they told us was 500 square centimeters. And so I got to do the 1 meter over 100 centimeters and square it this time. That gives me 0.0500 square meters. So the pressure I can calculate as the force, 588 newtons, spread out over, and we're saying this is kind of uniformly spread out. That gives us 11,760 newtons per square meter. So you can see the pressures can become pretty large. If you've got a modest force, but that force is concentrated so that it's acting over a really small area, you could have a pretty good, a pretty large size pressure. So I wrote it as newtons per square meter, and then I converted it into pascals. Now, over here, I guess I did this. Oh, this is the 1 foot. Yeah. So this is 2 feet, and then what happens if I'm just standing on 1 foot? Well, it's, the gravitational force acting on me hasn't changed. I'm still going to need 588 newtons of normal force to offset that gravitational effect on me. The area now is half as much, and so that's at 0.0250 meters squared. Putting that into my force over area, that is pressure. That works out to be twice as much. So now it's 23,520 newtons per square meter, 23,520 pascals. Okay. Now air pressure, and we'll get to this a little bit later, but atmospheric pressure is a good reference here. Atmospheric pressure turns out to be almost 100, well, not almost exactly, but it turns out to be roughly 100,000 pascals. 100,000. It's actually 101,300. And atmospheric pressure varies also from time to time. This is about 1/4 of an atmosphere of pressure. So those are going to be units for us too, is how many atmospheres of pressure, given that Earth's atmosphere at the surface of the planet has a pressure of 1 atmosphere. All right, what about this pressure in fluids? So going back to this really quickly. Okay, so I stood on 1 foot, and I got the pressure to go up to 23,520 pascals. Ooh, what happens if I stand on my toes? What if I stand on just one set of toes? If I go up on my toes, can I stand? I guess I can. So if I stand on just one set of toes, the area gets much smaller, and that means that the pressure is going to get very large at those locations. So if you've got something where people are standing and they might stand up on their toes and put a lot of pressure, the material is going to have to be sturdy. What we saw in the last chapter is stress is actually in terms of pressure units. So if we have more and more force concentrated into a small area, going to be really large pressures. I remember, I think, reading this at some point that New York City, at least at one time, had a law about high-heeled shoes, saying that high-heeled shoes have to have a heel of at least a minimum area. And the issue was that because of fashion, high-heel shoes with really, spike heels had become popular, and it was tearing up the concrete sidewalks. Okay, so if you put, a modest amount of force, but you concentrate it into a really small area, you can stress out these materials and you can, you can fracture them. All right, pressure in fluids. Let's talk about this a little bit. So in a fluid, we could pick any location in a fluid and go, okay, what's going on in a fluid? Well, in a fluid, a liquid or a gas, you're going to have molecules that are bumping into each other. And what they've done here is they've put a little, they've designated a little piece of the fluid. So here is a little box that they've put around a certain section of fluid. And what happens is that piece of fluid is being pushed by all of its neighbors. Well, of course we could do that with any piece of fluid anywhere. It's not just the fluid in the middle that's under pressure, it's the fluid everywhere. So all the molecules are bumping into each other, everybody's exerting pressure. So the pressure is not just at the sides of the pressure is throughout. The pressure is throughout the material. Now we could measure the pressure by dropping an instrument into the fluid and maybe the instrument has some springs inside and it's compressible and it reports how much it's been, how much pressure is acting on it, how much force it's experiencing. But you got, think of that way. Wherever you are in the fluid, there's going to be a certain pressure there. This fluid is what we call static. A little later in the chapter, we'll look at some fluids that are in motion. But for now, we're going to stick with static. Now what they're saying here is the pressure is the same in every direction. That's not quite true, we're going to find out. It turns out that as you drop through a fluid, pressure accumulates. The upper fluid is resting on top of the lower fluid, which is resting on top of the lower fluid. So because of Earth's gravitational field, the pressure actually will increase as we drop to lower and lower elevations within that fluid. So at the top of this fluid, there's going to be atmospheric pressure, and then that pressure will increase, and that increase in pressure will be determined by how dense the fluid is. Okay. So because of gravity, we're going to have these different levels of different pressure, and the pressure from below is going to be a little higher than the pressure is from above. And since the pressure from below is just a little bit higher, right? At this elevation, the pressure is something, and then below that box that we've drawn, the pressure is a little higher. That's where our buoyant force is going to come from. So we're actually going to have a little bit of upward force on these. Now, to a good approximation, we're going to treat the pressure as uniform in all directions, but then we're going to come back and show that there are these effects as we drop lower in the fluid. Another issue going on here is the size of the container. The fluid is going to exert a force. The force that it exerts is perpendicular to the surface. It's perpendicular because the molecules are in random motion. And if there were a sideways component to that, then the fluid would not be static. Okay, so the argument here is because the fluid is static, the force that it exerts on the walls of the container are perpendicular. All right, let's take a look at pressure increase. So we've got some fluid here, looks like water. And what we're going to do is we're going to start, we don't have to start at the top, but they've done that here. So we're going to start at the top and work our way down. Now, we would call that depth, but it gets the symbol H, which means it's kind of the same thing as height, but it's kind of depth and height. They're vertical measurements on distances. Anyway, we're going to call this H, and we're going to think of, at least I'm going to think of H as, sometimes we'll think of H as positive in this direction, sometimes, we'll see how it works. So we'll keep track of directions as we move along here. And then there's a cross-sectional area of the object. So what we've got is an object with some cross-sectional area, horizontal measurements, and then a vertical measurement of H. What would the volume be? Well, the volume would be H times A. So here's the pressure now. Now the pressure at a depth H below the surface would be due to the weight of that fluid. So again, we've drawn this imaginary boundary around part of the fluid, and we can do a force diagram and say this amount of fluid has a certain mass to it, and so there's a gravitational force pushing it downwards. Why is it not accelerating downwards? And that's because the fluid below is pushing up, and that's going to come from the pressure. So they're going to do this really quickly. I'm going to come back and take a closer look with a force diagram. But the idea here is that the pressure at a depth of H is the force per area. Now the force can be written as pressure. Okay, so we got to get the mg in here. So the force is going to have to be equal to mg. For the m, here's the g. For the m, they wrote that in terms of density times volume. So this is density times volume times g. When they solve this, then the pressure, when we drop a distance h, the pressure is going to be rho g h. So we're going to make use of this formula a lot. Let's take it a force diagram and see if we can do this in a little more detail. So here is the fluid. Now you don't have to start at the top. What you can do is you can do this in terms of two different elevations within the fluid. I'll say the difference here is h. And then there's a cross-sectional area. There is fluid pressure pushing down from above. There is fluid pressure pushing up from below. Who's bigger? The pressure from below or the pressure from above? And what we had just talked about is, well, since there's a gravitational force acting on this section of fluid, it's a fluid sample that we're looking at here, there's going to be a force of mg downwards, and that's going to set up so that there's more pressure below. So the force pushing down from above, see there's more fluid sitting on top, pressure pushing down from above is going to be not as large as the force from below. The force from below has to be able to offset the force from above plus the mg of the sample. Now, here we go. So let me add these extra steps in. So they kind of jumped to the other formula here. So what we're going to do is we're going to take this force equation, which comes from the force diagram that we have here. Again, we've got F1, I guess the force diagram here. We've got F1 here, we've got F2 here, we've got mg down. This is how much force we're going to need. Now I can take that and divide everything through by area. So I'll divide through by the cross-sectional area. When I do that, force over area becomes pressure. And force 1 over area becomes pressure above. So now what we're saying is, here are these different levels of pressure within the fluid. So at level 1, there's pressure 1, and as I drop to level 2, the pressure has steadily increased. So that's what I tried to do in this force diagram. Here's the force from above due to pressure 1, and here is the force from below due to pressure 2. Here are the forces on the sides. Now at the sides, the pressures are getting smaller as we go up, so I kind of exaggerated that to show that effect. So those are going to cancel out in any case. But we could, and we will, in an example, calculate what's the net force acting from the side of a fluid. All right, so once we divide it through by area, and then we have mg over area. We got pressure 2 is equal to pressure 1 plus mg over area. Then what we're going to do is that step where we take the mass and we replace it with density times volume. So this is our volume right here, A times H. And so now I've got an AH times the density times the gravitational field, because it's mg, and then the A's cancel out. And so that leaves us with a very useful formula. It says that the pressure at a lower point in the fluid is equal to the pressure at some higher point in the fluid plus rho GH. Depends on the density of the fluid, the gravitational field, and the difference in elevation between the two pressure measurements. Now that's often written as delta P. So that says that the pressure is going to steadily increase as we drop through a fluid. It's a gravitational effect. The fluid is sitting on top of other fluid, on top of other fluid, and the gravitational effect is squeezing everything together. And that sets up this pressure throughout. The delta P is equal to rho GH. Now when we get down to individual levels, if we want to integrate over the pressure, we can do that. So for integration needs, this formula becomes, the infinitesimal increase in pressure depends on the density of the fluid times the gravitational field times dx or dy. I think the book is using dy, and again, I don't mind using x for vertical distances, so that's what I'm doing here. Okay, that's important. That's an important diagram. Make sure you understand what's going on there. So this is just kind of repeating the same thing. If we have a sample of the fluid, here is the pressure. Here is the force from below, pressure times area. Here is the force From above. So I see how they're doing this. This dp is actually going to be a negative value. What they've done is they've defined y from the bottom upwards. It's a little different definition of a coordinate system. Since they're defining upwards as the positive direction, so this is dy is getting, y is increasing, and we've got a steady number of dy's along here. What they're going to end up with is the pressure is decreasing as we move up through the fluid. Now that works well. We could also define the top part as y equals 0, and then treat y as increasing downwards, and then that minus sign would be gone. So again, we've seen this over and over. Pay attention to the signs. You have to really ask yourself, do I have the sign set up in a way where as this variable increases, as y increases, does p increase or does it decrease? And it depends on how we've defined directions. Okay, and then they're carrying out the integration. So here's what they're doing. They're starting at the bottom here, working their way up. And what they're doing is, I guess they're integrating between this location and a location at the top. Now notice that once they get to the top of this fluid is still in contact with the atmosphere. So there's still atmospheric pressure at the top. The pressure does not drop to 0. But what they've done then is they've integrated dp from a lower pressure to a higher pressure. And then on the other side, the minus sign is there because as you move it upwards, they're calling that the positive y direction, and the pressure is going to drop off. And so they're going to integrate from y1 to y2. This is rho g dy. When they carry out that integration, they're going to get the formula that we saw above. Now, where this integration, you're asking yourself, well, why would we do an integration? As long as the fluid density is uniform, as long as rho is uniform, you really don't have to do that. If the gravitational field and the density of the fluid are uniform, it's not a big deal. So you don't have to carry out the integration because the density factor and the gravitational field factor both come outside that integral sign, and then it's just a matter of going back to our original equation. Now, if we're doing atmospheric pressure calculations, that's not going to work. As you go up in the atmosphere, the density does not remain the same. The density drops off, and it drops off significantly. At some point, you're in outer space, right? And there's no density of air at all. And so for calculations in the air, that's going to become important. Also with water, if you're going really deep into the ocean, the pressure increases are going to result in a density variation. The water is going to be denser once you get to higher and higher pressures. So you're going to need something to put into the formula in order to carry out an integration. All right, here we go. Here's the water tower. If you're out in the Central Valley driving through, every town you come through, every city has these water towers set up. And what's happening there is by having a water tower set up at this elevation, that is able to maintain pressure in all the water lines. It's not like, where should we store all of our water? Let's build a big tower and just store the water there. There's no need to build a big tower. You could store water near the ground. But the problem would be, if we had this reservoir of water at the ground here, then the water coming out of those pipes would not be at very high pressure. It seems kind of remarkable, but here's how it works. As we drop in elevation, the pressure of the water in this pipe is going to go up. We can treat it, water in a pipe can be treated pretty much as a static fluid. And you're thinking, wait a minute, I turn the faucet on and the water comes shooting out. It's not static. Well, actually it is. The water mains are so large that when you turn your faucet on, sure, you can see this stream of water coming through at a good speed, but it's not very much. If you go out and dig up the street and look at the water mains, the pipes bringing the water in, the speed there is hardly going to be affected. So to a good approximation, we can just use static pressure formulas and say that H, in this case 30 meters, we're going to get 30 meters worth of pressure increase. Now 30 meters, that's like 100, that's a good tall tower. Now, here we don't see the towers because we just build the reservoirs up in the hills. So if you're wandering around up in the hills, driving around from time to time, you'll run into a reservoir of water, and that's how we maintain pressure. So you need the water stored at a higher elevation so that there's plenty of pressure for the users. And the idea is that those users, if I see a reservoir, which users are going to be supplied by that reservoir of water, well, it's going to be, 30 meters downhill somewhere. It's going to be a good distance downhill in order to have that pressure available. So here's the example set up. So here's the water tower. What we can do is we can start with atmospheric pressure. Now, again, I think I wrote it out here. I want to get these numbers out here right away. So here is atmospheric pressure. I'm going to call that P naught. That is 1 atmosphere. And I'm going to say those are actually pretty handy units to work from. So atmospheres are good too. Now 1 atmosphere is defined to be 101,300 pascals. So that's a rough estimate as what typical air pressures or atmospheric pressures are going to be at the ocean level. Let's see, so the water pressure in those, see this water, I put a bigger pipe. So I put a really larger pipe and it goes down into the water main under the roads or underground. And then here it is heading out to the users, and then here is a pipe coming in. And it's always remarkable to me too to think that, every time I turn on water, where is that coming from? Try to imagine the path that water is coming from, and then think that your water coming into your home is connected to pipes. Those pipes are connected to other pipes that are connected to all the water faucets everywhere. Everywhere through the neighborhood, everywhere through the city. And so so what I'm really interested in terms of how much pressure is there going to be when I turn on the faucet, is what is the elevation difference between where this faucet is located, what's its elevation compared with the top of the water level wherever the water is being stored. Maybe it's in a water tank like this, maybe it's in a reservoir somewhere, but that's the distance that we're looking for. Now, in this case, they're telling us it's 30 meters. This is Earth, that's the gravitational field. Now, the density of water, if you remember, is 1,000 kilograms per cubic meter. So that's a good amount of density, right? And so the delta P is going to be given by rho GH. And that says here's the density, here is the gravitational field. We're treating the density as a constant. It's a good approximation over these distances. The gravitational field is constant, and then the height. It says that this tower is setting up a pressure of 294,000 pascals. Now that would be 294 kilopascals. Now this is what's called gauge pressure. Let's go back and check. This is a delta P. This is above and beyond atmospheric pressure. So if I get a gauge out to measure my water pressure, more likely than not, it's not measuring what we call absolute pressure. It's measuring what we call gauge pressure. How much pressure is there above and beyond atmospheric pressure? So for example, if I get a pressure gauge out and I measure the pressure in my bicycle tire when it's flat. So let's say my bicycle tire goes flat, I get the pressure gauge out, what does it read? And it reads 0. But wait a minute, it's not really 0. The pressure inside the tube is 1 atmosphere, and the pressure outside the tube is 1 atmosphere, and that's why it's flat. It's not that the pressure has really gone to 0. So the pressure gauge is telling me that compared with atmospheric pressure, the pressure inside my bike tire is no different. It's zero difference, and that's why the tire has not maintained its shape. I have to go to a higher pressure than atmospheric to have the tire pumped up and to be useful. So we could do this either way. We could say this is gauge pressure, 294. Now that's about what? That's about 3 atmospheres, let's say. We said 100, right here, roughly 100 kilopascals is the equivalent of 1 atmosphere. So that's about 3 additional atmospheres of pressure due to a water piping system that works off of a difference of height of 30 meters. Now, let's see, what's an atmosphere is about 15 pounds per square inch. Those are English units. So 15 pounds per square inch, that would be like 45 pounds per square. That sounds like water pressure, you know, in some pipes. That's pretty good water pressure. So again, about 3 atmospheres or about 300 kilopascals. Now we can add on, if we want absolute pressure, what is the actual pressure that the fluid is under? Then we got to add on this background of air pressure, of atmospheric. So we'll add that on, and that boosts us up to 395. So the absolute pressure is 395 kilopascals. The gauge pressure is 294. You can buy absolute pressure gauges too. So those are, but it's more common that we measure things relative to atmospheric. Let's see, what else do we have here? So here again is this water tower. Here's this height of 30 meters down to the water main. And what's happening in terms of air pressure? I was just curious. We just did this example. So we said that the difference in water pressure from here to here worked out to be 294,000 pascals. Well, what's the difference in air pressure? Isn't there a difference in air pressure when I drop down 30 meters? And there is. We can use the very same formula. Delta P is equal to rho GH. Now the difference between air and water, among other things, is that the density of air is much, much less. The density of air at 20 Celsius and a pressure of 1 atmosphere is 1.20 kilograms per cubic meter. So this mixture of oxygen and nitrogen has a density of 1.20 compared with a density of 1,000 for water. And that says if we calculate the increase in air pressure as we drop from the top of the tower down to the 30 meters down to the ground level, that's only 353 pascals. So what happens in these problems? Let's go back and take a look. Notice that I neglected the change in air pressure. I did not take that into account. So actually the air pressure would also increase, and that would be a few hundred pascals. But since the water is 800 times more dense, or more than 800 times more dense, this is only like 1 part in 800 of an effect. So it's like a 1 in 1,000 part effect, and we often neglect that. So we have to be careful. I always think it's a good idea to remind yourself, oh yeah, there's a change in air pressure taking place too, and then maybe take a look at that and say, yeah, but it's a small number. This 350, it just doesn't really come into play here because this is 294,000. Okay, so again, we often neglect air pressure, but keep that in mind. There are going to be instances where we want to bring that back. Now here is here's an aquarium window. So you're walking through the Academy of Science or something in Golden Gate Park. Maybe there's an aquarium there with a window, and you can kind of stare at all the fish. And what you know now from chapter 13 is, wait a minute, how can that window be holding back all that water? Isn't that an enormous amount of force? Because that water pressure is going to be pretty large. We're going to have a pretty good sized water pressure. And so what we can do is this. It says here in this example, there's a window, it's 3 meters this way, it's a meter this way. The window begins at a certain depth below the top, and oh look, they seem to have gone back and used our convention of y is equal to 0 at the top, and then measuring the distance downwards as positive. Now, what we're going to have to do for the pressure calculation on this, I can't use a constant value of pressure. So the pressure is actually going to be varying. Pressure is going to be, the pressure is going to be a good value here, and then it's going to get higher and higher. And so what they want us to calculate is the force. So let's see how we would set that up. Get a good look at that aquarium window, and here we are. So here's the aquarium window, and again I'm using X, I apologize. So this is the arrow down to here, so I'm treating increasing X in this direction. Well, what we're going to need to do in this case is we've got the pressure, as we drop, the pressure is going to be given by rho gx. Now we've got a couple choices here. Do we want to work in terms of delta P, or do we want to work in terms of absolute pressure? So I'm going to try and do this kind of both ways. I'm going to say that the absolute pressure at a certain depth is the air pressure, the atmospheric pressure that we started with at the top, plus rho gx, where x is the distance below the surface that we're looking at. And so what's going to happen is the values of x, and I could have drawn some arrows here, so draw an arrow downwards like they did for the x. That's a little section of dx, and we've got to add together all those dx's between the value of x1 and x2. So that's how I've set up the integration. The integration is going to come from integrating all the little forces at each level. Now the force at each level, dF, is going to be equal to the pressure at that location times dA. Now pressure is not an infinitesimal. The pressure is a finite value. So that little bit of force, the force is only small because dx is very narrow. So that's going to be equal to, the pressure is P naught plus rho gx, and then the area here, let's take a look at the area. The area is given by L times H, but since it's d area, it's going to be L times dx. So the area of that little strip right there, where we're measuring the force, is L times dx, and plug that in, and then integrate from x1 to x2. Now when we do that, we find out that we really have two different integrations going on. We have the first term in the integration is keeping track of the fact that there was already atmospheric pressure. So that's kind of handy. What I can do is I can take this integral and divide it into two pieces and say this is keeping track of the background atmospheric effect. This is keeping track of the delta P effect of the water. So this is going to be the delta P effect, water. This is going to be the background atmospheric pressure. And when I carried out the integrations, there is, this is just dx. That just integrates out to be h. But this is, there's an extra factor of x here. And that extra factor of x is, the factor of x is coming from the increasing pressure. So this is keeping track of increasing pressure. When we integrate that, we get 1/2 x squared. So the force acting on that window is going to be, there's a part due to the presence of atmospheric pressure. That's going to be P naught times LH. Now LH, if you remember, that's just the area of the window. Plus this additional pressure due to the presence of the water. So that's what's going to determine, and that's got some x squareds in it we got to plug in. So let's do that. Now I rewrote this. I said that the force acting on that window, and here's the window right here. So this is a side view of that window. And what's happening is there's water pushing against it. Now remember, the force of the water is perpendicular to the surface, and the pressure is going to be increasing. So if I think of this as dF, 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 the dFs are getting bigger on the water side. Now on the other side, I've got air, and there's going to be a dF, 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 dF from the air, what's going to happen here, I think I showed that with the arrows, is that at the top, the two pressures match. Right at the top surface of the water, both inside and outside, the pressures would match. Oh, that's not true though, huh? Because we're already below the water surface. So by the time we get to the window, the pressure inside is going to be greater. Okay, so well, let's see what we get. So the air pressure, it turns out, could be written as atmospheric pressure times, or the force, not the pressure, but the force. Atmospheric pressure times area. The additional force due to the presence of the water is given by rho g, x2 plus x1 over 2 times L, x2 minus x1. The reason I did that is x2 minus x1 is the height. And so that can be combined with the L value here to give us the area. So these two terms work out to be area. And then x1 plus x2 over 2 is average. So it says that, another way to think about this is that the force, here is the atmospheric pressure effect. To get the force of the water, what we could have done is measured the pressure halfway along the window. So that's saying that if I pick the average value right here in the middle, if I take x1 and x2, add them, divide by 2, that, since the pressure is increasing linearly, taking that pressure at the average location will work. Okay, so if I know that in advance, I guess I don't have to do the integration, but you want to do the integration to try it out. So that's another way of thinking about this. Now here is the increase, or here is the total force. It's from here, so I'm calling this delta F. So if I think of this as kind of the background atmospheric pressure, how much additional force am I getting when the aquarium is filled with water? So when it's filled with water, I'm getting this much additional force, this piece over here. That can be calculated as, I guess we've got the values here. So let me come to here. Here is the P naught. Here is the average depth. The average depth is at 1.5 meters. So we took the 1 and the 2, we took the average value, and the density times G times X at that location is 14,700 pascals. So notice, we're not terribly deep. It's only a meter. And as a result, the pressure is not super large, 14,700 pascals. And then we have to multiply by the area, which is 3 square meters. So we're going to get an additional force on that aquarium window when we fill it with water of 44,100 newtons. So that's how we have to design the window. Now, what we're thinking here is that, well, what's going on the two sides then? If we think of the air pressure pushing against that window from the outside, the air pressure itself is 303,900 newtons. So, you know, the outside air is 304 kilopascals. The water from inside, once I've added on the atmospheric pressure, is 348,000. So those are absolute pressures of air from the outside, water from the inside. So those are the absolute pressures, and I think it's good to practice that. Now, if I'm designing this, I don't have to make the window strong enough to withstand 348,000 newtons as long as air pressure is maintained outside. Now, we're not going to, you know, it's a science museum, right? We're not going to create a vacuum out here, eliminate the air. If we eliminated the air, this pressure would go away. And then we would have to build the window strong enough to withstand that much force. Okay, so again, we just have to build the window strong enough to withstand the additional 44,100 newtons that the water pressure is going to add to the left side of that window, the way we have that drawn. Okay, pressure in fluids. So we've been doing this. Now we're going to be looking at atmospheric pressure and elevation effects. If we move up through the atmosphere, the density of the air drops off. So the air becomes less and less dense. And that means that we're going to have to do some kind of an integration to keep track of atmospheric pressure as we go to higher and higher elevations above the Earth's surface. Now, we should be somewhat familiar with the atmosphere. So the atmosphere primarily consists of nitrogen molecules and oxygen molecules. Now, nitrogen and oxygen molecules, they're diatomic. So it's N2 and O2 molecules. And by number, about 78% of those molecules are N2, and roughly 21% of the molecules in the air are O2. Now, the other relatively large component of the air, a couple more, is argon. That's kind of interesting. We have about 1% of the atmosphere is this inert gas, or noble gas, I guess is what they're called now. And then what happens is this complicates things, and it's water. Water is variable. So if I'm at a very, very dry location, the air is very dry, what that said, and the humidity is, basically 0%. That means that there are very few water molecules in the air, but as you know, we can also go to very humid locations where there's a lot of water molecules in the air. At relatively high temperatures and 100% humidity, water presence in the air can go as high as 4%. So that's variable. Notice that these have been calculated as dry air, and then this complicates things. So as the amount of water goes up, then these all scale back a bit with varying amounts of water. Now, carbon dioxide is a big concern to us as far as its presence in the air. Carbon dioxide and its greenhouse effect can be important, significant, even though it's only at a level of about 400 parts per million. And maybe you've heard that number before. It was a few years ago when Earth, the atmosphere crossed the 400 parts per million of CO2. 100 years ago, it was, I think, below 300 parts per million. So again, it's not a huge number. It's only 0.040%. It's only 4 parts per 10,000 You have to go through 10,000 air molecules to find 4 carbon dioxides. But it's a significant effect. So we are sensitive to this amount of carbon dioxide, and the CO2 levels are headed upwards. It's an issue that that we all need to address, and you guys especially as scientists and engineers got to be thinking in terms of that number, pretty much whatever type of work you end up in. Anyway, so there's the carbon dioxide. Now here's the gravity, and the gravity is pulling all the air molecules in. Now with air, air is a gas, and the gas is easily compressible. And that means the air at the surface is compressed, it's denser than it is up above. Now you guys don't have to know this. We're going to come back and do this in Physics 4B, but just in case you've seen this in your chemistry classes or your physical science classes, I'm going to introduce what's called the ideal gas formula. And that says that for air, we can relate, for a gas, we can relate the pressure, the volume, the temperature, and the number of air molecules by a relatively simple formula. This is something called the number of moles. I'm guessing you've seen that in physical science classes, maybe, maybe not. Again, it's not required at this point. We can calculate the number of moles in a sample by taking the mass of the air sample, or the gas sample, dividing through by what we call the molar mass. Now the molar masses, I should have written them out over here. You can determine those from the periodic table. For N2, the molar mass would be 2 times 14 is 28. For oxygen, it's 2 times 16. Again, it's just reading off the periodic table. Gives us 32. Argon has a molar mass of 40. Water has a molar mass of 18. Carbon dioxide has a molar mass of 44, I think, 44. Anyway, for us what's important is that I can determine the density of the air as a function of pressure. So here is our pressure formula that we had developed, and we said this is minus rho g dx. Now I am going to call x upwards positive for this, and so I'm going to put the minus sign in to remind me that the pressure is going to drop off as we go higher. Now, the reason this would be difficult to integrate is because the pressure is varying, and now by having a formula, using the ideal gas formula, we now have an ability to write the pressure, or the density, in terms of the pressure. So now the density can be rewritten as PM over RT. PM over RT. R is just a constant, so that can be written pretty easily. Let's just decide on maybe 0 Celsius would be 273 kelvins. We have to use an absolute temperature scale. The factor of G is still there, and then the molar mass of air. So when we rewrite this differential statement in terms of infinitesimals, we need to get all the pressures to the same side. So I'm going to bring this factor of pressure, which was in the numerator, bring it over to the other side and put it in the denominator. Okay, and so what we're going to be left with is dP over P is equal to minus molar mass times the gravitational field over the big R constant, temperature dx. That's what we're going to integrate, is that statement below. And here's what it looks like. So what we can do is take the dP over P, the pressure, integrate from, now I'm going to integrate from atmospheric pressure at the surface up to some pressure at a higher location. Now notice this side is integrating from higher values to lower values. That's not a problem. That's taken care of with the minus sign. So that minus sign is kind of telling us that when the right side of the equation increases, the left side of the equation is going to go down. So I'm going to integrate this left side. That becomes the ln of p, from p naught to p. And then for logarithms, I can evaluate those two limits. That'll give me the logarithm of p over p naught. Meanwhile, on the other side, I don't have any x dependence other than dx. All of these are constants. So that's a pretty simple integration. We'll just integrate x, or dx, from 0 to x. That'll just leave us with a factor of x. Now again, x here is height above the surface of the Earth, is the way we've set this up. So that becomes minus mg over rt times x. And what I've done is I took the mg rt and combined that into a constant. And here's how I did that. Here's the value of g, here's the value of big R. The temperature needs to, we said 0 Celsius. Now, the atmosphere doesn't have a set temperature as you go up. It doesn't stay constant. So that number could be changing significantly. But we're going to consider it as if it's staying right at 273. Now that's kelvins, and I'm guessing you've seen that in other physical science classes. If not, again, we'll see this in Physics 4b when we do thermodynamics. Now the molar mass of air, and we'll see this in Physics 4b too, 29 grams per mole, very close, so 0.0290 kilograms. I needed to get that into kilograms, and now I've defined a constant, a scaling factor, as being RT over mg. Now why did I define that? Well, I can then write the pressure equation as, I can take out the mg RT, replace it with 1 over A, and that gives me x over A. That tells me that A has units of distance. Okay, and it's going to become a scaling factor. So when I exponentiate this equation, I now have the pressure is equal to P naught times E, I exponentiated, to the minus x over A, where A is a scaling factor. And plugging all these numbers in, I ended up with something very close to 8,000 meters, or about 26,000 feet. So it says that there's a scaling factor for how the atmospheric pressure drops off, and it follows. This is based on an exponential, a base E exponential, the natural base to use for exponentials. And so with E, when x is equal to a, that would become e to the minus 1. E to the minus 1 is 37%. Now, you may be familiar with half-lives. When something decays, how much time does it take for half of it to be gone? This is based on base 2. It's not 1/2. It's when does the pressure drop to 1 over E? And notice that atmospheric pressure drops down to 1 over E of its surface value. That's only 37%. And that happens at 26,000 feet. So if you've climbed to 26,000 feet elevation, or if you've flown at an elevation above that, the atmospheric pressure at that point would only be 37% of what it is at the surface. So, when you're flying in a plane, you're probably at 35,000 feet, and the outside air pressure is, 25, 30% of what it is at the surface. It's much, much lower. It's significantly lower. So, now I can adapt that. I could take the scaling factor and set it equal to 1/2, and then solve for x. So if we're working in base 2, that would say half the atmosphere would be gone by the time we had gone to an elevation of 5,550 meters. Okay. Anyway, that's what the drop-off looks like. It's a bit of a rough approximation on the formula, but it gives us an idea of how air pressure drops off with elevation. Now, the highest elevation I've ever climbed to is Mount Wheeler in Great Basin National Park in Nevada near the Utah border. And that was at about 18,100 feet, so it comes in, I'm sorry, it's not the 18,000, it's the 13,100 feet. Sorry. So 13,100 feet, that's about 4,000 meters. So at the top of that peak, atmospheric pressure was only 60% of what it is at the surface. Only 60%. Now, I didn't notice that so much, but so that's kind of interesting. The atmospheric pressure can drop off so much as we climb. All right, I think it looks like it's probably time to stop there. So if you guys have questions, which I'm guessing you do, stop by office hours and we'll get those looked at. Okay.